Hello student, I am Nirmala Morade, Department of Mathematics from S.V.K.T College, Devali Camp, Nasik. In last lecture, we learnt linear combination of vectors. If we consider V is a vector space, and take some vectors from V. V1, V2, V3 bar, Vn bar, these are the vectors in V. Then the expression this is called the linear combination of the vectors V1, V2 bar, V3 bar up to Vn bar. If we consider the set of all linear combinations, here K1, K2, Kn are all scalars. Now consider the set of all such a linear combinations of these vectors. Set of all linear combination, all possible linear combination of these vectors, then this set is a subspace of V, and it is the smallest subspace of V containing all these vectors V1, V2, Vn. That is this set, suppose I denote this as a W. W is the smallest subspace of V containing the vectors V1, V2, Vn. That is, there is no other subspace of V consisting all vectors V1, V2 up to Vn and the set W itself. So last lecture we learnt about this and the problems or examples related to the linear combination. Now in today's lecture we are going to study what is meant by span of S, where S is any subset of a vector space V, that is the subspace generated by given vectors. We consider some examples related to it. After watching this video, students are able to understand definition of subspace generated by the given vectors or given subset of vector space V. And secondly, it is students are able to solve the problems whether given set is span the given vector space or not. So let us first see what is the definition of span of given set or the given vector. So first we consider V is a vector space. Let S containing these vectors V1 bar, V2 bar up to say Vn bar. So it is a subset of V. Obviously it is a non-empty subset of V containing these n vectors. Then we consider the set of all possible combination of all linear combination of these vectors, that is we consider the set W. It is a K1 V1 plus K2 V2 bar up to Kn Vn bar, where K1, K2, Kn are scalars. So as we know that this is a subspace generated by, this is the smallest subspace containing the vectors V1, V2, Vn. That is, first of all, it is a subspace of V, and this subspace is called the subspace generated by the vectors V1, V2, Vn, or it is called span of S. It is called span of S. And now it is denoted by the symbol span of S, or sometimes it is also written as span of V1, V2 bar and Vn bar. Okay, again we recall the definition. Subspace generated by given set or the vectors. So first of all we consider V is a vector space. S is a set containing the vectors V1, V2, Vn, which is a subset of V. Then set of all possible linear combination of these vectors in S. That is, we consider K1 V1 plus K2 V2 up to Kn Vn, where K1, K2, Kn are the scalars. So as we know that it is a subspace of V, and this subspace is known as a subspace generated by S. Now it is denoted by span of S or span of V1, V2, Vn. So in short, W is a subspace generated by S, means every vector in W can be written as the linear combination of vectors in S. Every element in W can be written as linear combination of vectors in S. So now let us consider some simplest example. So first we start with R2. So we know that we consider the vector space R2 with standard operation, that is component wise addition and component wise scalar multiplication. We know that it is set of all ordered pair xy such that x and y are real numbers, and we consider the operation as a standard operations on R2. It is a vector space. Then take the unit vector, standard unit vectors. E1 bar, it is also denoted by I bar, which is equals to 1, 0, and second is E2 bar, or it may be denoted by the symbol J bar, which is equals to 0, 1. So this set spans R2. This set spans R2. We can easily check that every vector in R2 can be expressed as linear combination of these two vectors. So now for that we consider the arbitrary vector in R2. So I consider this vector xy. So xy vector can be written as E1 times x and y times E2y. We can easily check whether this linear combination equals to xy. Okay, now check this. So for that we consider x into E1 bar plus y into E2 bar, which is equals to, keep x as it is, E1 is 1, 0 plus y as it is, put the value of E2 which is 0, 1. So this is same as, do the scalar multiplication, component wise scalar multiplication. So x into 1 is x, x into 0 is 0, plus y into 0 is 0, y into 1 is y. Now add these two vectors. So the addition of these two vectors is x plus 0 is x, 0 plus y is. So here if I consider any arbitrary vector in R2, it can be expressed as the linear combination of these two vectors E1, E2, and therefore this set, that is set of standard unit vectors of R2, spans R2. So we say that this spans R2. So just extend this for R3. So unit standard vectors for R3 also spans R3. So if we consider R3, so we know that R3 is nothing but the set of triplets, set of all order triplets x, y, z, such that x, y and z are real numbers. This is a vector space with respect to the component wise addition and component wise scalar multiplication. Consider the set of standard unit vectors. They are denoted by either symbol ijk or E1 bar, E2 bar and E3 bar. So we consider here E1 bar, which is same as 1, 0, 0. Next E2 bar 0, 1, 0 and E3 bar, which is 0, 0, 1. So you can easily check here the arbitrary vector x, y, z can be written as x times E1 bar plus y times E2 bar. Okay, you can denote here just E1, E2, E3 also, or we can put the bar over each vector also, plus z times E3 bar. So you can do it, you can check this easily. So here this vector is a linear combination. Any arbitrary vector of R3 is a linear combination of these 3 unit vectors, standard unit vectors. So this set spans R3. So similarly, if we consider R raised to n, R raised to n nothing but set of n tuples where each xi belongs to R. Then if we consider the set of unit standard vectors, that is E1 bar, which is 1, 0, 0, E2 bar 0, 1, 0 and so on, and last is En bar 0, 0, last term is 1. So in general, remember EI is a vector, unit vector whose ith component is 1 and remaining components are 0. So if you write in general, its only ith component is 1 and remaining components are 0. These are the unit vectors, standard unit vectors in R raised to n, and this set spans R raised to n. So we say that here it is spans R raised to n. So this is about R raised to n. Now next consider the another next standard example is the example of polynomial of order less than equal n, that is Pn. So we know that Pn is the set of all polynomials in single variable. I write here x with degree less than equal n, including 0 polynomial. We include the 0 polynomial also here. So we know that this is a vector space with respect to addition and scalar multiplication of polynomials. Again see, Pn is a vector space. It is the set of all polynomial in single variable with the degree less than equal n, including 0 polynomial. So we can easily check that the set containing the vectors 1, x, x square up to x raised to n. This set spans Pn. And now it is easy to check. So for that we consider an arbitrary polynomial in Pn and write that arbitrary polynomial in terms of linear combination of these vectors. So I consider the arbitrary polynomial in Pn a0 a1x plus a2x square continue up to an x raised to n. It is the set of all polynomial of degree less than equal n. So this is an arbitrary polynomial in Pn. So this polynomial can be written as a0 into 1 plus a1 into x plus a2 into x square continue n into x raised to n. So if we observe this side, or we can observe this one, it is a linear combination of the vectors 1, x, x square and so on up to x raised to n, because the coefficients of the polynomial are nothing but the scalars. So if you pick any polynomial from Pn, it can be easily expressed in terms of the linear combination of these vectors. So we say that these sets spans Pn. So now we will consider the another example of matrices. So consider the set of 2 by 2 matrices with real entries. As we know that it is a vector space with respect to addition of matrices and scalar multiplication of a matrix. So it is a vector space with respect to these two operations. So now we write one set here containing the vectors, say 1 0 0, another vector 0 1 0 0, so these are the 4 vectors in this set. So if I consider the arbitrary element from this set, that is the set of 2 by 2 matrices with real entries. So we consider a 2 by 2 matrix with entries A, B, C, D. So this set can be written as A times, this is the first entry, so we write this matrix whose first entry is 1, other entry is 0. Next, plus B, so we choose the vector whose second A22 entries, A12 entry is 1, other entries are 0, that is this matrix 0 1 0 0. Similarly write the next one, so D times 0 0 0 1 and plus C times 0 0 1 0. So if you solve the right hand side, you can easily check that this addition is same as this matrix. So here A, B, C and D are the scalars. So we can say here every 2 by 2 matrix with real entry can be written as linear combination of these 4 matrices. So this set spans the set of 2 by 2 matrices with real entries. So these are the some standard examples. So we can easily remember these standard examples or the sets which spans the vector space. Now we consider the another examples related to this. Okay, this is our example. Determine whether the given set S containing 3 vectors 1, 1, 2, second vector is 1, 0, 1, third vector is 3, 1, 2, spans R3 or not. So now suppose I want to check this spans R3, that is we must determine an arbitrary vector in R3 is a linear combination or is a linear combination of the vectors in S. So for that consider one arbitrary vector in R3. So suppose we consider ABC be an arbitrary vector in R3. Now express this vector in terms of linear combination of given vectors in S. So write here ABC is equals to some scalar. I take the first scalar as a K1 into first vector 1, 1, 2 plus write the second scalar K2, multiply the second vector 1, 0, 1 plus K3 and the last vector. Now this is one equation and we check whether this system has a solution or not. So for that solve the right hand side. So keep the left hand side as it is ABC, this is equals to, multiply this vector by K1, so K1, next K1, 2K1 plus here multiply K2 by this vector, so K2 into 0 is K2, again it is 0 and similarly do the last term. So it is 2 times K3, comma K3, 3 times K3. Now add all these 3 vectors simultaneously. So I keep the left hand side as it is, and this is equals to. So addition of these 3 vector is nothing but a vector whose first component is addition of all the first components of these 3 vectors. So which is K1 plus K2 plus 2K3. Next component is addition of the second component of each vector. Okay, so K1 plus 0, no need to write 0. Next is K3, comma. Last one is the addition of third components. So 2K1 plus K2 plus 3 times K3. So this is the addition of all these 3 vectors. So as we know that when 2 vectors are said to be equal, if they have the same component or the corresponding components are equal. That is, first component equals to first, second equals to second, and so on. So here we just equating all the components. So we will get here K1 plus K2 plus 2 times K3 equals to A. That is, we equate the first component here. Now equate the second component. So here this is the second component, K1 plus K3 is equals to B, and now equate the third component, so which is equals to twice K1 plus K2 plus K3 is equals to, this is the third component of this side, so which is C. So equating this, we will get one system here. Always remember, so we get a linear system. In this linear system, the unknowns are K1, K2, K3. So we have to find the solution for this system. Since in this system there are 3 variables and 3 equations, so we find the determinant of coefficient matrix here. So determinant of coefficient matrix, we denote A, which is equals to, in first row we write the coefficient of coefficient of K1, K2, K3 from first equation, so which are 1, 1, 2. From second equation, 1, the coefficient of K1 is 1, K2 is absent, so 0, and K3 is 1 times K3, so coefficient is 1. So do the same thing for writing the last row, 2, 1, 3. Now solve this determinant, which is equals to, so 1 times, when we solve the determinant, we use the first row. So 1 times multiplication of these 2, which is 0, minus multiplication of this, which is 1. Next, minus 1. So 3 minus 2 plus 2 times 1 minus 0, which is equals to minus 1 plus 2, which is equals to 0. So here determinant equals to 0. Now observe, this is a non-homogeneous system. A system like this one, Ax equals to B. We know that for non-homogeneous system, and if determinant of A is not equals to 0, then this system has unique solution. Now the non-homogeneous system Ax equals to B with determinant of A not equals to 0, then system has unique solution. This system has unique solution, and if determinant not equals to 0, next one is determinant equals to 0, then in this case there are 2 choices, either system has infinitely many solution or no solution. Okay. Now since here determinant is equals to 0, so we can't say that every system has solution. Every system has solution, that is every equation has a solution. And since we can't say that every equation has no solution, therefore we say here the given set do not span R2. The given set do not spans R3. If determinant is equals to 0, then given set do not span R3. Or we can easily solve this system by Gauss elimination method also. And since if system has solution for in every case, then we say that it spans R3. But in many cases, if system has at least no solution for at least one triplet ABC, then we say that this given set do not span R3. So here determinant equals to 0. So the given set do not span R3. So let us consider the another type, same type example but with different vectors. So remember, suppose we want to show that given set spans R3 or not, or in any other polynomial, in case of any other vector space. To determine whether the set spans R3 or not, take an arbitrary vector from that vector space. Write that vector as a linear combination of given vectors. Here we have to given 3 vectors, so I have to write the 3 vectors here. Solving this equation, we will get one system. Check system has a solution or not. If system has a solution for every ABC, then we say that the given set span R3, otherwise not. Here determinant equals to 0, so we say that here there is a possibility of getting no solution for some pair for some triplet ABC. So this set do not span R3. So now let us consider another example. Now this is the simplest example. So again question is same, determine whether the set S spans R3 or not. So we must determine whether an arbitrary vector from R3 is expressed as a linear combination of these 3 vectors or not. So for that, take again arbitrary vector, say ABC from R3. Write this ABC as a linear combination of all these 3 vectors. So I put here K1 times first vector 2, 2, 2 plus K2 times second vector and K3 times third vector. Okay. So solve the right hand side. You can write this side directly also. The first component of this addition is 2 times K1 plus 0 times K2. So no need to write that value. Next 0 times K3, so which is also 0. So there is only one term here. Write the second term of the addition, 2 times K1, 1 times K2 plus 1 times K2 plus 0 times K3. So no need to write that term also, comma. Write the last components, 2 times K1, 1 times K2 plus 1 times K2 plus 3 times K3. So these 2 vectors are equal. So equating the components, so we will get here. I write this vector first and then write this one. Therefore, 2K1 equals to A. Next, 2K1 plus K2 equals to B. And third component is here. 2K1 plus K2 plus 3 times K3 is equals to, write the third component of this side, which is 3. Now find the determinant of coefficient matrix. So suppose coefficient matrix is A, its determinant is 2, then 0, 0, next 2, 2, 0, next one is 2, 1, 3. So now see, it is a upper triangular matrix. You can find its determinant 2, this is 6, minus 0 is 6, next terms are 0 here obviously, so no need to calculate this one. So here determinant is 12, which is not equals to 0. Okay, I think, okay, this one is wrong. This coefficient is 1. So this is 1. This multiplication becomes 3. Answer is 6. Okay, so again it is not equals to 0. Do the calculation carefully, it is very important. So here determinant not equals to 0. So for non-homogeneous system, Ax equals to B. If determinant not equals to 0, if and only if this system has unique solution. This system has unique solution. That is, for every ABC, you will definitely get a solution. And that is, every triplet ABC can be expressed as a linear combination of these 3 vectors. And therefore, we say that the given vectors span R3 or given set spans R3. So now consider another more example which is related to the polynomial. Now this is our another problem. Determine or check whether the given set of polynomials spans Pn, not Pn, P2 or not. So again we consider here an arbitrary polynomial from P2, and we show that arbitrary polynomial is expressed as a linear combination of these 3 vectors. So starting with, so take the arbitrary polynomial from P2, which is a plus bx plus cx square. So this is a polynomial from P2. Express this polynomial as a linear combination of these 3 vectors. So consider a plus bx plus cx square is equals to, I take the scalars as a k1, k2, k3. So k1 into first polynomial plus k2 into write the second polynomial, which is 3 plus x, plus k3 into third polynomial, which is 5 minus x plus 4x square. So as usual, solve this equation. We will get one system and check whether system has a solution or not. If system has solution every time, then given set spans P2, and if system has no solution at least in one case, then we say that the given set do not span P2. So keep the left hand side as it is. Now solve this side. So I multiply this polynomial by k1, so it becomes k1 minus k1x plus 2k1x square. Similarly solve the remaining part. 3 times k3, k2, k2 into x plus 5 times k3 minus k3x plus 4 times k3x square. We just simplify the bracket, we multiply the polynomial by the scalars. Now collect the similar terms. So we maintain the same sequence. First term is constant, then term of x, and then term of x square. So we first collect the constant terms. So this is our first constant term, this is next, and this is the next. I write all these constant term in one bracket. K1 plus 3k2 plus 5k3. Okay, I put all these constant terms in one bracket, then I collect the terms of x and take x as a common. So we double underline the terms of x. This is our first term of x, this is second, and this is the third. And from all these terms, we take x as a common and write all the remaining here. So if we take x common, remaining is minus k1. here remaining is K2 and next remaining is minus K3. Okay, do the same thing for the remaining terms. Remaining term contains x square. Take x square common and write all the remaining terms in this bracket. So remaining terms are 2x1, then this is a term of x square. Okay, there are only two terms of x square. So these two polynomials are equal polynomials. So we know that polynomials are equal if and only if they have the same constant term, they have the same coefficient of x, x square and so on. So equating this polynomial we get here, equate the constant term. Here constant term is a, here k1 plus 3 times k2 plus 5 times k3. Next equate the term of b, equate the coefficient of x. Here coefficient of x is b and here it is minus k1 plus k2 minus k3, and now last we have to equate the coefficient of x square. So we will get here c is same as 2k1 plus 4 times k3. Again you can observe here it is a system of linear equation. We check whether this system has a solution or not. So for that we find the coefficient of determinant of coefficient matrix, which is same as. So here always remember the unknowns are these scalars k1, k2, k3. So we write the matrix of coefficient of this system, which is 1, 3 and 5. Next one is minus 1, 1, minus 1. Next one is 2, 0, 4. Just write all these things carefully. 1, 3, 5, minus 1, 1, minus 1, 2, 0, 4. Now solve this determinant by regular method. So its value is 1 into 4 minus 3 times minus 4 plus 2 and plus 5 times 0, it is minus 2, which is same as 4. Then it is minus 2 and minus 3. So plus 6 and then minus 10. It is again 0 here. So okay, just do each and every calculation carefully, it is very important. So since determinant is equals to 0 here, indicates that this system has do not have solution always, and so this set do not span P2. So it is very important, do each and every calculation carefully. So in today's lecture we will study here, we have studied what is meant by set generated by the given vectors, as well as some examples related to it. So always remember, if V is a vector space and S is a set containing the vectors v1, v2, vn, then the set of all possible combination of vectors in S generate a subspace that is called the set generated by S. Thank you.